This is just going to provide a little bit of an overview about gases and gas laws. As you can see from this introductory slide, we use gases in a bunch of different ways. We can use it in the form of propane gas to heat our homes or cook on the grill. We use helium gas to make balloons float. We can also generate gas in cars when we want an airbag to kind of inflate very, very quickly for an accident. But we also know that gases are not always good. We generate carbon dioxide gas when we burn fossil fuels, and this actually contributes to global warming. Alright, this is just going to be showing some of the characteristics of all gases. We know that gases all are made of atoms or molecules. These are small spherical particles. Even though they're small, they do have mass. We demonstrated earlier in the course that air has mass by putting two balloons on the end of the meter stick, and we popped one of them, and we were able to see that there is definitely some mass in even the small amount of air that we had. But it's important to remember that gases do have large amount of empty space. It's not like a solid where these molecules are tightly packed together. The gases would take up the entire space of a container, as you can see in the picture here, and they will spread out. So that's going to contribute to some of the properties here of gases as well. Going along with what I just said, gases are easily compressed and can be expanded, and it has to do with this large amount of empty space. You put them in a container and they will spread out. The molecules of a gas will spread out to take up the entire space, but because there's so much empty space, we can put a little pressure on it and make those molecules come closer together. But you should realize that the molecules and particles of a gas are moving around constantly and very rapidly, and they're bouncing off the sides of the container that the gas is in. As you can see in these pictures, okay, these molecules of a gas are not just standing still. Imagine these molecules in this balloon constantly zooming around, bouncing off of each other, and keeping the shape of the balloon. This constant motion that is seen by gases brings us to the kinetic theory of gases, which basically explains the properties of gases and why they behave the way they do. And the kinetic theory of gases basically says that these particles, these molecules of a gas, are in constant motion, and they are just randomly banging off of each other, bouncing off the sides of the container. It's very fast. They're hitting each other, and this is what's going to allow gases to have pressure, so that a balloon doesn't collapse in upon itself. These molecules are bouncing off the sides and keeping the shape, but it's also, because they are moving around constantly, there's all that empty space, we can also compress gases here. So this is known as the kinetic theory of gases. Imagine all these particles in this box constantly zooming all over the place, bouncing off each other just randomly, and you have a good idea then of the kinetic theory of gases. Because the particles are constantly zooming around and bouncing off each other in the sides of the container, gases have pressure. And as you can see here, this is the force exerted by the gas on an object. So when the gas particles are zooming all around, bouncing off the sides of the container, they are creating a pressure there. And it's all due to the kinetic theory of gases, these collisions, and these particles constantly just moving around and banging off each other and the sides of the container. We use a barometer to measure the atmospheric pressure. If you ever hear on TV a meteorologist talking about the barometric reading, and this basically exists due to the air molecules striking other objects in the atmosphere. There are some units of pressure here that exist for gases, and these three conversions you're required to know, and you can add them to your list of conversions that we've learned and used throughout the course. The first one is 1 atm is equal to 760 millimeters of mercury. Atm just stands for atmosphere. 1 atm is also equal to 760 torr, and 1 atm is equal to 101.3 kilopascals. So again, you are required to know them. We can use them in conversion problems. You could be given one unit in a problem and need to convert to another in order to be able to do the problem. So it's very important that you know how to do these conversions. But also to reiterate, STP is 0 degrees Celsius and 1 atm. That's standard temperature and pressure. We talked about that earlier in the course. At the bottom here is an example. In the example, you're asked to change or convert 3,400 millimeters of mercury to atmospheres, ATM. So you could see, you set up the dimensional analysis like we've always done. You start with what you're given, 3,400 millimeters of mercury on the top. So you need millimeters of mercury on the bottom in order for it to cancel. Well, we know that there's 760 millimeters of mercury for every 1 atmosphere. Your units will cancel, and you'll be left with atmospheres. Don't forget, correct sig figs, and you just did a conversion problem involving gas pressure. So now we're going to get into the gas laws, and as you see here from this slide, there are different factors that will affect a gas, and these include pressure, the amount of the gas, temperature, and volume, and we can kind of use these in our gas law problems. And how a gas actually responds to changes in these particular factors actually can be predicted using the various gas laws. So what you'll see on the next few slides are the definitions of the different gas laws and then problems using those gas laws, as well as examples. The first gas law we're going to look at is Boyle's law. Boyle's law is actually an inverse relationship, and it involves pressure and volume. The idea of Boyle's law is that if you increase the pressure, then the volume of the gas will decrease. It's very important that you understand here that the temperature is constant. Okay? From this, then, we can create or set up an equation, which is P1V1 equals P2V2. This would be the pressure and the volume before, and this would be the new pressure and volume. And you'd have to be given 3 of the 4 values in order to solve for one of the ones you don't know. The easiest way to think about this is, imagine you took a balloon, okay, and I put a lot of pressure on that balloon. I squeeze that balloon. What would happen to the size of that balloon? It should decrease. The volume should go down. It should get smaller, because as I increase the pressure, the gas molecules in there, the empty space, okay, you're compressing that gas and you're making the balloon smaller. This is a very good demonstration of Boyle's law. The pictures you see here on the slide with the marshmallows is also another good illustration. If you put marshmallows in a syringe and you decrease the pressure, basically you create a vacuum and you decrease the pressure, the size of the marshmallow should get larger, because as you decrease the pressure, the volume should increase. And that's what you see happening in this picture right here. We did this in class. We put the marshmallow, the peep, in the device. We removed the air with the vacuum, and the marshmallow actually got larger. So that is Boyle's law. Let's look at an example of a Boyle's law problem. It says a balloon is filled with 25 liters of air at 1.0 atm pressure. If the pressure is changed to 1140 millimeters of mercury, what is the new volume? In this problem, you're given pressure and volume. Therefore, that makes it a Boyle's law problem. You're going to have to use P1V1 equals P2V2. It's very important that you pay attention to what is given in these problems, because that's going to tell you which law you're dealing with and therefore which equation you need to use. It's also important that you pay attention to your units. I can see that there's going to be a problem because I'm starting with ATMs for pressure, and in the problem they change to millimeters of mercury. So I'm going to have to do some kind of conversion in order for this to all work out. So let's actually go and do the problem. Make this smaller here. Okay, we know that we're using the equation P1V1 equals P2V2. All right, I have the option of converting ATMs to millimeters of mercury or millimeters of mercury to ATM. Since it's just 1.0 ATM, that's a very easy conversion. In order for ATMs to cancel, I know it has to be on the bottom. There's 1 ATM for every 760 millimeters of mercury. ATMs cancel, one on the top, one on the bottom. You're left with 760 millimeters of mercury. So now I can actually start the problem. There's 760 millimeters of mercury. The volume from the problem is 25 liters. The new pressure is 1140 millimeters of mercury. And we don't know the new volume, so we're just going to leave it as V2. When you do the math and actually solve for this, it comes out to be roughly 16.66 liters. With correct sig figs, comes out to be 17 liters. In the problem, your volume is in liters, so your volume in your answer is going to be in liters. It's also important that you pay attention that your pressure is both in millimeters of mercury, so they would cancel out. The next law we're going to look at is Charles' law. Charles' law is a proportional relationship between volume and temperature. And the whole idea here is that if you would increase the temperature of a gas, the volume of the gas should increase as well. It's important to note here that the pressure is constant, so we don't see that in our equation, and the equation we can use here for Charles' law is V1 over T1 equals V2 over T2. And remember, you need to have at least 3 of the 4 variables in order to be able to solve this equation. Something very important to note here is that for all gas law problems, the temperature must be in Kelvin. Okay? Even if you're given Celsius, you have to convert all temperature in the problem to Kelvin. So if you remember from earlier in the course, we said that degrees Celsius plus 273 will always give us Kelvin. So you may have to do a temperature conversion in these problems in order to successfully complete the problem. A really good example of Charles' law at work would be a balloon. Imagine if you had a balloon here and you cooled that balloon down. You took the balloon and you put it in a bucket of ice water. What would happen to the size of that balloon? Well, according to Charles' law, that balloon should shrink. And you can actually try it out. Okay, as you decrease the temperature of that balloon, okay, the volume of the gas inside the balloon would decrease as well. Think about it. Those particles are not going to be moving around as fast. They're not going to be hitting the sides of the container as much of the balloon. So the size or the volume of the balloon will actually decrease. Same thing in reverse would happen if you actually heated the balloon up. The volume of the balloon should expand and it would actually increase because the temperature increased. As you see here in the picture, what's happening is you could take a soda can, fill it with some water, put it on a burner, and heat it up. And as that liquid started to boil, you actually are generating gas in the can. It's vapor. And what you can do is then you can then take that can, put it in a cold water bath, and the can itself would collapse. Because what happens is you are decreasing the temperature of the gas in the container, therefore the volume is dropping, and it collapses the can. Let's take a look at an example of a Charles' law problem. The example says, what is the temperature of a gas expanded from 2.5 liters at 25 degrees Celsius to 4.1 liters at constant pressure? Again, you have to pay attention to what is given in these problems, and I can see that I'm given volume and temperature. Therefore, I know it's going to be a Charles' law problem, and I'm going to need to use V1 over T1 equals V2 over T2. But the problem here is going to be the temperature. You know that for all gas law problems, you must be in Kelvin. So I'll have to do a temperature conversion before I can actually start the problem. So let's make this smaller here, and let's actually do this problem. So before we begin, the 25 degrees Celsius needs to be converted to Kelvin. Okay, degrees Celsius plus 273 is equal to Kelvin. So I know that I'll be starting with 298 Kelvin in my problem. So now that I have my temperature in Kelvin, I can actually solve for this. And again, it's V1 over T1 equals V2 over T2. So now I'm just going to plug in and solve. My initial volume is 2.5 liters over the temperature, which we found to be 298 Kelvin, equal to 4.1 liters is my new volume, all over T2, the final temperature, which I don't know. When you actually solve this problem, do the math, you should get the temperature to be equal to roughly 488.72. But with sig figs, that brings us to 490 Kelvin. Again, it's important to remember that these problems are in Kelvin. So when you're solving, your units must match up. I have liters and liters for my volume, and I have to have my temperature in Kelvin. The next law we're going to look at is Gay-Lussac's law. This law also is a proportional relationship, but it is a relationship between pressure and temperature. The whole idea here is that as you increase the temperature, the pressure of the gas would increase as well. The volume is constant for this particular law, so you're not changing the volume at all. Therefore, the equation we can use for this is P1 over T1 equals P2 over T2. And since it's a gas law problem, it's important to remember that the temperature must be in Kelvin in order for you to be able to do these problems. A really good example of Gay-Lussac's law would be, think about what would happen if you heated an aerosol can, like a hairspray can. If you increased the temperature of that can by heating it, it could potentially explode because the pressure inside that can would be going up, and if you get it too hot, it could explode. Another good example of this is the sucking of the egg into the bottle. What you would do is you can actually put a match that's on fire in the bottle, put the egg, the hard-boiled egg, on top. What happens is, as the match burns out, the temperature inside the bottle starts to drop. Okay, it was warm because the match was burning. Well, now the air temperature is dropping. Well, since the air temperature is dropping, the pressure, therefore, inside the bottle is also dropping. And what happens is the pressure inside becomes less than the pressure outside. So the outside pressure is greater, and it forces the egg into the bottle. So those two examples are really good examples of Gay-Lussac's law at work. Let's look at an example of a Gay-Lussac's law problem. It says, what is the pressure inside a 0.250 liter can of deodorant that starts at 25 degrees Celsius and 1.2 atmospheres if the temperature is raised to 100 degrees Celsius? You have to note here that they're giving you some excess information in this problem. They're telling you the volume of the can of deodorant. The volume of the can of deodorant is not changing in this problem. Therefore, it's constant. So it does not play a role in our problem. Therefore, that makes this a Gay-Lussac's law problem because you're comparing pressure and temperature here only. You're not worried about the volume. So it's going to be a P1 over T1 equals P2 over T2. So let's actually set this problem up and see what we come up with here. Again, because this is a gas law problem, your temperature needs to be in Kelvin, and you have to get used to doing that. So we know degrees Celsius plus 273 is equal to the temperature in Kelvin. So the first one is going to be 25 degrees Celsius plus 273. That's going to be 298 Kelvin. That's what you are starting at. And then it says that it's raised to 100 degrees Celsius plus 273. So your final temperature in Kelvin would be 373 Kelvin. Now that you have your temperature conversions done, you can actually set up the problem. Again, it's P1 over T1 equals P2 over T2. Since your temperature is in Kelvin, you can go ahead and do this problem. You're starting at 1.2 atmospheres. And the temperature is 25 degrees Celsius, which we already calculated to be 298 Kelvin. And we are changing the temperature here to 100 degrees Celsius, or 373 Kelvin. But we don't know what pressure this would be at. So we solve for P2, and it comes out to be 1.5028 atmospheres. With correct sig figs, it's 1.5 atm. The next gas law we're going to look at is the combined gas law. This basically combines all that we've learned from Boyle's, Charles, and Gay-Lussac's law and puts them into one larger problem. It's important to note here that the number of molecules, or the amount of the gas, is going to be constant. But the equation we can use is P1V1 over T1 equals P2V2 over T2. So instead of just manipulating two of the variables, you actually have three things going on here. We have pressure, volume, and temperature involved. But again, it's a gas law problem, so your temperature must always be in Kelvin. So let's look at an example of a combined gas law problem. It says a 15-liter cylinder of gas at 486 kilopascals pressure and 25 degrees Celsius is heated to 75 degrees Celsius and compressed to 17 atmospheres. What is the new volume? So it's important to note here that you have to figure out that this is a combined gas law problem. You can see that there's volume involved, there's pressure involved, and there's temperature involved. And because all three are important, that means we're going to need to use the combined gas law of P1V1 over T1 equals P2V2 over T2. But before I can even get started with the problem, I actually have to do some conversions here. In order to do a gas law problem, I need to have my temperature in Kelvin. And right now, my temperature is in Celsius. So I'm starting at 25 degrees Celsius. So 25 plus 273 is equal to 298 Kelvin. That would be my starting temperature. And then it says that it's heated to 75 degrees Celsius. So 75 plus 273 is equal to 348 Kelvin. Again, degrees Celsius plus 273 will give you the temperature in Kelvin. But I also have one more conversion here. They are giving me pressure to start in kilopascals, but then they're telling me that it's compressed in atmospheres. So I have to do a conversion to either get both of them to being kilopascals or both of them to being atmospheres. I've decided to convert the 486 kilopascals to atmospheres. So in order for my units to cancel, I know that kilopascals must be on the bottom, and the conversion we know is that there's 1 ATM for every 101.3 kilopascals. My kilopascals will cancel. I'm going to be in ATMs, and with correct sig figs, it's 4.80 ATMs. So now I can actually go through and do the problem. P1V1 over T1 equals P2V2 over T2. I'm going to be solving for volume 2 because I don't know the new volume. So my initial pressure we calculated was 4.80. I'm not going to include the units here to save some space. My initial volume was 15 liters. And my initial temperature was 25 degrees Celsius or 298 Kelvin. And I change it to 17 atmospheres of pressure. I don't know the new volume, but the new temperature is 348 Kelvin. So you actually have to solve this problem for the new volume. And when you actually do that with correct sig figs, you get 5.0 liters for your answer. It's important that you do the math right here. You can multiply 4.80 times 15, divide that by 298 Kelvin, then multiply both sides by 348 Kelvin to get rid of it from the right side. And then you would simply divide both sides by 17 atmospheres, and that would give you the 5.0 liters in correct sig figs. All right, so let's look at two examples here involving gas laws. And in these problems, you're not told which gas law you're using, so you actually have to read the problem and figure out which gas law is involved, and that'll determine which equation you're going to use. So the first example says bacteria produce methane gas in sewage treatment plants. If a bacterial culture produces 60.0 milliliters of methane gas at 700.0 millimeters of mercury, what volume in liters would be produced at 760.0 millimeters of mercury? So I have to figure out which law I am using here. Well, I can see that I have volume of a gas at a specific pressure. And then I'm looking for the new volume at a new pressure. So pressure and volume are the only two things involved here. Therefore, by definition, that's Boyle's law. So I have to use P1V1 equals P2V2. Now that I identified the law that I'm using, I can actually go ahead and solve this problem. So I know I'm using P1 V1 equals P2 V2. There's no mention of temperature. It's not involved, so I don't need it. So let's just plug in. All right, our initial temperature, our initial pressure is 700.0 millimeters of mercury. Our initial volume is 60.0 milliliters. And we are changing it to 760.0 millimeters of mercury pressure. But we don't know what volume that will be. So when you solve this equation for V2, you get roughly 55.263. Now, it's important to pay attention to what your units are. In the equation, your volume is in milliliters, therefore your volume 2 is going to be in milliliters. In the problem, they ask for liters. So, you're going to have to do a conversion here. We know that there is 1 liter for every 1,000 milliliters, so this is actually a very simple conversion. You need milliliters to cancel. Okay, so 1 on the top, 1 on the bottom. There's 1,000 milliliters for every liter. And this gives you, with correct sig figs, 0.0553 liters. So that's the first problem there. Let's look at the second problem and see what is going on. It says a pressure cooker raises the temperature of its contents by keeping the contents under pressure. The volume of the cooker is 4.0 liters. Steam at 100.0 degrees Celsius and 1.00 atm usually cooks the food. If the cooker is placed at 1.15 atm, what will the temperature of the steam be in degrees Celsius? So you have to look at this problem and see which gas law you're going to be using. I can see that they give me volume. I can see that I'm given temperature and pressure as well. So initially you might think that this is a combined gas law problem, but it's not, because the volume of the cooker is always going to be 4.0 liters. The volume of the cooker is not changing, it's constant. Therefore, you would not need to use the volume in this problem at all. So you're just using pressure and temperature, and by definition that's Gay-Lussac's law. So you're going to need to use P1 over T1 equals P2 over T2 in order to solve this problem. So, to solve this problem, we already know we're using P1 over T1 equals P2 over T2. Because it's a gas law problem, and I'm given degrees Celsius to start, I need to convert that to Kelvin. So 100 plus 273 is equal to 373 Kelvin as my initial temperature. So now I can plug in. I'm starting at 1.00 atmospheres. The temperature is 373 Kelvin. We've changed the pressure to 1.15 atmospheres. And we want to know what the temperature will be. So when you solve this for T2, you get 428.95 Kelvin. But the problem asks for the temperature in degrees Celsius. So we use degrees Celsius plus 273, okay, is equal to Kelvin. When you solve for degrees Celsius with correct sig figs, you get 156 degrees Celsius. So it's very important that you pay attention to the problem and pay attention to your units in the problem in order to get the correct answer. Now we're going to look at the ideal gas law. And this gas law is very important because it includes all 4 things that can affect a gas. So the equation for the ideal gas law is PV equals nRT. And basically now we are not restricted by the conditions of STP. STP is 0 degrees Celsius and 1 atm. Well, we are no longer going to be restricted by those conditions. So let's look at what this actually means. P is going to be the pressure, V is going to be the volume, okay? N, as you can see, is the number of moles of the gas you're dealing with, or if you're not given the number of moles, if they give you the grams, for example, you can do grams over molar mass, because grams divided by molar mass is the number of moles of a particular substance. So if they give you grams in the problem and you know what the substance is, you can find out its molar mass, and therefore you would have N. R is a constant. It's the ideal gas constant. R is always equal to 0.082 liters times atmospheres divided by Kelvin times mole. These units are important because they ensure that all the other units in the problem will cancel out. So R is always equal to this amount, all day, every day. Just like we've seen constants earlier in the course with some of our light calculation problems, R is a constant and will never change. So you need to know what R is. And then T would be the temperature. And again, it's a gas law problem, so it must be in Kelvin. So what's really the difference here between an ideal gas and a real gas? Well, ideal gases follow the gas laws at all conditions of pressure and temperature. Okay? Ideal gases don't really exist because they assume that particles have no volume and that there's no attractive forces between the particles of a gas. But this is not true. So ideal gases don't really exist. And what you'll find out here is that the reason we use this is because it's a very close approximation. So we assume this to be true, even though technically ideal gases don't really exist. Real gases, though, do have volume. Okay, we've seen that earlier in the course when we did our air has mass and volume demo. Okay, you can blow up a balloon. Okay, so real gases do have volume and they do attract to each other. And the only way you can really have gases being ideal is at very low pressures or high temperatures. If the pressure is very, very low, the particles of the gas don't really come in contact with each other, so you don't really see those attractive forces. So the only way you can actually have gases being ideal is at very low pressures or high temperatures. So there are some limitations here to the ideal gas law. Again, it only works well at low pressures and high temperatures because that's when a gas will act ideally. Okay, if you look at the picture here, under very, very high pressure, okay, the volume of the gas is significant. Okay, you see in this picture there's a lot of pressure being applied on that gas, so the volume is significant. Also, since the molecules of the gas are in such a small amount of space, they're more likely to come in contact with each other and there could be some attractive forces. Whereas if you're under very low pressure, okay, you're less likely to have those gas particles coming in contact and having attractive forces, and the volume of the gas is going to be negligible. So most gases do not behave ideally above 1 atmosphere of pressure. Okay, we're looking for low pressures here. And it does not work well near the condensation condition of a gas because those would be the conditions where you would start to have some attractive forces. So ideal gases really don't exist because we know that gas molecules do take up space and attractive forces do exist. Otherwise, we wouldn't get liquids. So we can actually take a gas, compress it down, and get it to be near conditions where we can actually get it to turn into a liquid. But the math is very easy with these problems, and it's a very close approximation. So we do assume gases are ideal, even though there are limitations of this law. Let's look at two examples here of the ideal gas law. The first example says, determine the volume occupied by 2.34 grams of carbon dioxide gas at STP. You are kind of keyed in that this is an ideal gas law problem because you're dealing with an amount. When we did combined gas law problems, the amount of the gas was constant. So in this particular example, they're giving you an amount. That is an indication you're going to need to use the ideal gas law, PV equals nRT. It's very important that your units match up for these problems as well, so that is something we got to look at. We know we're using PV equals nRT. R is a constant. R is always 0.082 liters times ATM over moles times Kelvin. So I need my volume to be in liters, my pressure to be in atmospheres, I need my amount to be in moles, and my temperature to be in Kelvin in order for the units to work out with R. Well, it says that it's at STP. Well, STP is 0 degrees Celsius and 1 ATM. So ATM works for R, but degrees Celsius does not. It needs to be in Kelvin. So Celsius plus 273 gives us our temperature in Kelvin. N is the number of moles. Well, in this problem, you're given the number of grams. As I showed on the previous slides, that in order to use N, it has to be moles or grams over the molar mass. So we have to find the molar mass here of carbon dioxide. Carbon dioxide is CO2. There's 1 carbon times 12 is equal to 12. There's 2 oxygens times 16 for each oxygen. That's 32. So when we add this up, there's 44 grams per mole. Okay, so for every 1 mole of carbon dioxide, there's 44 grams. Now we have enough information to do this problem. The pressure is going to be 1 ATM, because we're at STP. The volume, okay, is what we're trying to find out. N is usually number of moles or grams over the molar mass. Well, they told you there's 2.34 grams, and we found the molar mass. Therefore, if you actually did this calculation, your units would be in moles. So 2.34 grams divided by 44 grams per mole times R, which is 0.082, and your units are liters times atmospheres, all over moles times Kelvin, times temperature, which is 273 Kelvin. And if you look, all your units work with R, okay, so that when you solve for volume, because of the units on R for volume is liters, volume would also be in liters. So when you solve this equation for volume, you get 1.19 liters for the correct sig figs for this problem. The second example says if I have 2.4 moles of a gas held at a temperature of 97 degrees Celsius and in a container with a volume of 45,000 milliliters, what is the pressure of the gas? Again, you're dealing with moles. That tells you you're going to have to use the ideal gas law, PV equals nRT. But this problem is a little bit different. We have to do some conversions first before we can use the PV equals nRT for this particular problem. First, my temperature is 97 degrees Celsius, needs to be converted to Kelvin. So degrees Celsius plus 273 comes out to be 370 Kelvin. But my volume, according to R, must also be in liters, and they are giving me 45,000 milliliters. So I have to get my volume to be liters. Well, in order for my units to cancel, milliliter on the top, milliliter on the bottom, we know there's 1,000 milliliters for every liter. Therefore, my volume in this problem is 45 liters. Now that all my units work and will cancel, now I can actually do the problem. We don't know what the pressure is going to be. We do know the volume is 45 liters. nRT, N is the number of moles, 2.4 moles. R is always equal to 0.082. It's got to keep its units, liters times ATM, all over moles times Kelvin, times the temperature of 370 Kelvin. When you solve for pressure, it's equal to 1.6 atmospheres. Okay, your units of pressure on R are atmospheres, so when you solve this equation for P, your pressure units are going to be atmospheres as well, and that's to the correct sig figs. Dalton's law involves what happens if you mix a bunch of gases here. So what Dalton's law says is the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. So the whole idea here is you take all the pressures of each of the individual gases that you're mixing, add them up, and you'll have your new total pressure of all the substances you mixed together. So as you can see from this example, if I took a gas that had a pressure of 2 atmospheres, mixed it with another gas that had a pressure of 1 atmosphere, and mixed it with another gas that had a pressure of 3 atmospheres, when I mix them all together, I add up the partial pressures and I get the new total pressure of the mixture of gases. So it's 2 plus 1 plus 3. That gas would have a new pressure of 6 atmospheres. All you do is add up the partial pressures of the individual gases and you get a new total pressure. That's Dalton's law. So let's just look at a quick example of Dalton's law. It says nitrogen, helium, neon, and argon are placed into a container. The partial pressures of each are as follows. Nitrogen has 80 kilopascal pressure, helium is 73 kilopascals, neon is 49 kilopascals, and argon is 108 kilopascal. They want to know the total pressure in the container. Well, if you add up the partial pressures of each of the individual gases, you'll have the total pressure of the container. So, 80 plus 73 plus 49 plus 108 gives you the total pressure of all those gases mixed together, 310 kilopascals. This slide is just going to very quickly differentiate between diffusion and effusion. You may remember diffusion last year from biology. The whole idea with diffusion is that a substance will try to move from an area of higher concentration to an area of lower concentration. So a substance will spread out. So if you look at this particular picture, there's a particular gas here where these molecules are in red, right? They're very highly concentrated, they're close to each other. So after diffusion takes place, they have spread out and they have moved apart from each other. Okay, this is different from effusion. Okay, effusion is when a gas is confined to a container that has a small opening. Molecules will randomly encounter the opening and pass through it. So a really good example here is with a balloon. A balloon has very tiny openings, and inside that balloon is a gas. Well, as those gas particles are zooming all around, bouncing off the sides of the balloon, occasionally they come in contact with one of those small openings and the gas molecule will pass through it. And over time, you can see this taking place because if you blow a balloon up, leave it for a few days, you come back, it's going to be smaller. And that is due to a fusion that was taking place. It's all random as those molecules are bouncing off the sides. When they hit one of those small openings and they can actually effuse through it, okay, they will escape the balloon. This is the difference between diffusion and effusion. Very quickly, I'm going to mention Graham's law of effusion. And Graham's law of effusion basically states that the rate at which a gas will effuse is inversely proportional to the square root of the gas's molar mass. So the basic gist of Graham's law here is that the lower the molar mass of a gas, the faster it's able to effuse. Okay, so if you actually look at this graph here, it makes it a little bit easier to understand. Okay, as you can see here, look at hydrogen gas, H2. Okay, the time it would take H2 to effuse is much quicker than, say, carbon dioxide. Well, compare the molar masses. Hydrogen gas, H2, the molar mass would be 2 grams for every mole, whereas the molar mass of carbon dioxide would be 44 grams per mole. So the lower the molar mass, the faster it will effuse. Think about it. Those molecules are going to be smaller. Okay, they're going to be zooming around pretty fast. They're going to be able to effuse through an opening much faster. So if you put hydrogen gas in a balloon, which we did earlier in the course, okay, it would effuse out of the balloon faster than, say, another gas. So if you filled up 2 balloons of equal size, one with hydrogen gas, one with carbon dioxide gas, and put them next to each other and weighted, the balloon with the hydrogen gas in it should be smaller over time than the balloon with the carbon dioxide gas in it, because the balloon with the hydrogen gas will be undergoing effusion at a much faster rate because hydrogen has a lower molar mass than the carbon dioxide. That's the whole gist of Graham's law of effusion.